So, let's go. You wake up one morning and read that scientists found an object in space the size of a city that outweighs the sun. And then you keep reading and realize that's number 10 on the list. Here are 10 objects in space so massive they break the laws of physics. Number 10, Stephenson 218, the star that ate Saturn's orbit. Most stars, when you look at them, are points of light, distant, small, polite. Stephenson 218 is none of those things. It's a red supergiant sitting about 19,000 light-years away in a crowded, dusty corner of the galaxy where measurements are hard and the stars are dying. And by current estimates, it is the largest star we have ever found. Its radius is approximately 2,150 times the radius of the Sun. That number doesn't mean anything until you put it somewhere familiar. If you replaced our Sun with Stephenson 218, its surface would extend past Mercury, past Venus, past Earth, past Mars, past the asteroid belt, past Jupiter, and stop somewhere near Saturn's orbit. The entire inner solar system, gone, swallowed. 10 billion copies of our Sun would fit inside it by volume. 10 billion. And yet, standing on a hypothetical planet nearby, you probably couldn't see it with your naked eye. Its surface temperature is only around 3,200 Kelvin, cool for a star, deeply red, almost infrared. It glows more than it blazes. It's a slow, massive, smoldering giant. Here's the uncomfortable part. Light takes about 8 minutes to travel from the Sun to Earth. It would take almost 3 hours to cross the equator of Stephenson 218. A beam of light moving at 300,000 kilometers per second needs 3 hours just to get from one side to the other. Now, and this is important, these measurements are contested. Another famous giant, UY Scuti, used to hold this record at roughly 1,700 solar radii. Then a satellite recalibrated its distance and the number collapsed to around 750. Stephenson 218 hasn't had that reckoning yet. The current figure is the best estimate we have. It might change. But even if it does, even if the real number is smaller, what remains is a star approaching the theoretical maximum size for stars of its type. It's at or beyond what stellar physics says should be possible. And that's the question this video keeps asking. Not just how big can things get, but what happens when something exists past the point where it's allowed to exist. Buckle up. Number 9. Neutron stars. A teaspoon that ends worlds. Forget size for a moment. Forget it completely. Because the next object on this list is only about 20 kilometers across. Smaller than most cities. If you drove past it on a highway, it would be gone in your rearview mirror in under a second. It also weighs more than the Sun. A neutron star forms when a massive star dies. The outer layers explode outward in a supernova. The core collapses inward, so fast and so violently that protons and electrons are crushed together into neutrons, packed wall to wall, held up by nothing except a quantum mechanical rule that says identical particles refuse to share the same space. That's it. That's the only thing between the core and total collapse. A rule, a principle, the universe's version of a building code. The density that results from this is genuinely incomprehensible. 1 teaspoon of neutron star material weighs approximately 1 billion tons, not the whole star. A teaspoon. That's more than the combined weight of every single car on Earth, compressed into something you could hold in a spoon. If you dropped that teaspoon, it would fall through the floor, through the ground, straight through the planet, and keep going. The surface gravity is around 200 billion times Earth's. A mountain on a neutron star can be no taller than 5 millimeters. Anything higher collapses under its own weight. The escape velocity from the surface is roughly half the speed of light. The fastest known neutron star spins at 716 rotations per second, with its equatorial surface moving at 24% of the speed of light. These objects also have a hard limit. There is a maximum mass a neutron star can reach, called the TOV limit, worked out originally by Oppenheimer and Volkoff in 1939. Push a neutron star past roughly 2 to 2.3 solar masses, and the quantum rule breaks down. Gravity wins. The star stops being a neutron star and becomes something else entirely. A black hole. The floor gives way. That limit is not precisely known, because we don't fully understand what's happening inside a neutron star. Whether the core contains a superfluid, whether strange quarks appear, whether normal matter even exists in there anymore, genuinely unknown. The interior of a neutron star is arguably the least understood environment in all of physics, something so dense it breaks the concept of matter, something with a hard ceiling on its own existence. And that's number 9. Number 8, SGR 180620, the magnet that rewrites chemistry. On December 27, 2004, something happened 50,000 light years away. A star the size of a city cracked, its crust shifted by about 1 centimeter, and in the next 1/5 of a second, it released as much energy as our sun emits in 250,000 years. The blast traveled outward at the speed of light. By the time it reached Earth, it was a wave of gamma rays that flipped our upper atmosphere from nighttime mode to daytime mode in an instant. It overwhelmed satellites. Scientists watching the sun with dedicated solar observatories saw it. It was so intense that it reflected off the surface of the moon. A star 50,000 light years away, roughly halfway across the Milky Way, bounced light off the moon. The starquake that caused it would have registered as magnitude 23 on the Richter scale. The largest earthquake ever recorded on Earth was magnitude 9.5. The Richter scale is logarithmic. Magnitude 23 is not 23 divided by 9.5 times as powerful. It's incomparably, absurdly more powerful. There's no useful human frame of reference. This is SGR 180620. It's a magnetar, a neutron star with a magnetic field exceeding 10 to the power of 15 Gauss. Your credit card gets erased in a field of about 50 Gauss. An MRI machine runs at around 30,000 Gauss. The magnetar runs at 1 quadrillion Gauss. It is 10 billion times stronger than the most powerful MRI ever built. Get close enough and the physics stops working the way you're used to. At 3,000 kilometers away, still far enough that the object looks like a pinpoint of light, its magnetic field begins pulling every atom in your body into elongated shapes, stretching them along the field lines. Hydrogen atoms, normally spherical, become needles. The chemistry that keeps you alive depends on atoms having predictable shapes. Those shapes stop existing. You don't survive this, you don't even make it to the surface. On the surface itself, the periodic table is essentially meaningless. The rules that govern how atoms bond, how molecules form, how matter behaves, overridden by a magnetic field so strong that space itself behaves differently. There's a phenomenon called vacuum birefringence, where the magnetic field is intense enough that even empty space becomes optically anisotropic, meaning light splits into 2 modes that travel at slightly different speeds. This has been confirmed by observation of another neutron star using the Very Large Telescope. Space near a magnetar is not the same as space everywhere else. The researcher, Victoria Caspi, one of the world's leading magnetar scientists, put it plainly. Magnetars are the only deep space objects that directly affect Earth, from 50,000 light years away. Imagine what it's like up close. The universe has rules about matter. A magnetar doesn't care. Number 7, TUN 618. The black hole, bigger than all our stars. Somewhere about 10 billion light years from here, in the direction of a constellation called Canis Venatici, there is a black hole. You can't see the black hole itself. What you can see is the light from gas falling into it, a quasar blazing at 140 trillion times the brightness of the sun. That light left this object when the universe was less than 4 billion years old, when the cosmos was still young and chaotic and building itself at full speed. The black hole at the center of TUN 618 has a mass of up to 66 billion solar masses. Not 66 solar masses. Not 66 million. 66 billion. That's more mass than all the stars in the Milky Way galaxy combined. Its event horizon, the point of no return, has a diameter of about 2,600 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. The event horizon of this black hole is 2,600 times that. It would swallow our entire solar system more than 40 times over. If you pointed a flashlight directly across it, the light would travel for weeks before reaching the other side. Gas spiraling into it falls at 10,500 kilometers per second, 3.5% of the speed of light. Here's where it gets philosophically strange. In 2015, a physicist named Andrew King worked out the theoretical maximum mass a black hole can reach through normal accretion. the process of eating gas from a surrounding disk. His answer, for a non-spinning black hole, was around 50 billion solar masses. The mechanism involves the innermost stable orbit of the disk, expanding as the black hole grows until eventually it gets pushed out past the self-gravitational radius of the material, meaning the disk tears itself apart before the material can fall in. Accretion stops. Growth stops. The black hole can't get bigger through this process. 2N 618 is 66 billion solar masses. It is, according to that calculation, impossible. The most likely explanation is that it's spinning very fast, which raises the limit. Alternatively, our models of how accretion disks work are incomplete. Either way, scientists had to invent a new category to describe it. Supermassive black holes are the usual giants. 618 is now called an ultramassive black hole, a classification that didn't exist before this object required it. And it will still be here, barely change long after everything else on this list is gone. Models predict it will take approximately 1.3 times 10 to the 99th years to evaporate via Hawking radiation. The black hole era of the universe, a period when black holes are the dominant objects in existence, begins around 10 to the 40th years from now. 618 will outlast that era. It will outlast essentially everything. Something that shouldn't exist, outliving everything that does. Number 6, IC1101, the galaxy that committed 100 trillion murders. Imagine a galaxy, a spiral probably with arms and dust lanes and a busy core. That's the Milky Way. That's what most people picture. IC1101 is nothing like that. It sits about 1 billion light years away, a dead golden enormous elliptical galaxy at the center of a massive galaxy cluster. There is no spiral structure, no dust lanes, no new stars forming. There's nothing young inside IC1101. It contains approximately 100 trillion stars, between 250 and 500 times more than the Milky Way, and every single one of them is old. The galaxy is yellow-red in color because all the blue short-lived stars burned out long ago. What you're looking at is an ancient object that has spent billions of years doing one thing: eating. IC1101 grew to its current size by consuming other galaxies. Dozens of them, Milky Way-sized galaxies, absorbed whole, their stars stripped away and added to the pile. Its core alone spans 13,700 light-years, larger than the distance from our Sun to the center of the Milky Way. Its full halo extends roughly 4 million light-years out from the center. If IC1101 replaced the Milky Way, it would engulf both Magellanic Clouds, the entire Andromeda Galaxy, the Triangulum Galaxy, and all the space between them. At its center sits a black hole somewhere between 50 and 70 billion solar masses, potentially rivaling TON 618. Except this one is dormant, quiet, it fed, and now it's done. The radio source at the core still flickers. The black hole still accretes at around 450 solar masses per year, which sounds enormous until you realize it's a dying ember compared to what it once was. There's a detail about the core that astrophysicists call a stellar mass deficit. The center of IC1101 has been scooped out. 500 billion solar masses worth of stars gone. Not destroyed. Ejected. When two massive black holes merge during a galactic collision, they spiral together and slingshot nearby stars outward at enormous velocities. Billions of stars, launched into the outer galaxy or into intergalactic space. The core of IC1101 is a graveyard of past mergers, its center hollowed out by its own violence. Its black hole, incidentally, is technically too massive for the galaxy around it. The expected relationship between a black hole's mass and its surrounding galaxy, what astronomers call the M-sigma relation, predicts a much smaller black hole for a galaxy with IC1101's properties. The black hole overshot. Nobody knows exactly why. An object that became the largest through consumption, whose central black hole broke the rules for its own formation, and whose core is a monument to everything it destroyed. Number 5, El Gordo, the cluster that shouldn't exist yet. When astronomers cataloged galaxy clusters, they expected to find large ones. That's fine. Big structures exist, but big structures take time to build. Small things merge into bigger things, slowly, over billions of years. You can't rush it. The physics of gravitational collapse has a pace. El Gordo, formerly known as ACT-CLJ-0-1-0-2-4-9-1-5, violated that pace. It is a collision between two massive galaxy subclusters, not a finished object but a crash in progress, caught mid-impact. The hot gas between the clusters glows in X-rays and lags behind the galaxies, because during a collision the galaxies pass through each other like ghosts while the gas actually collides and slows down. The gravity, however, follows the galaxies, not the gas. Meaning, if you map where the mass is and where the gas is, they're in different places. The gravity is where the gas isn't. That's dark matter, visible through its absence, written in the separation between two crashing clusters. Its total mass is around 3 quadrillion solar masses. For context, the entire local group, the Milky Way, Andromeda, the Triangulum Galaxy, and roughly 80 smaller galaxies is worth a few trillion solar masses. El Gordo is 1,000 times more massive than all of that combined, and it formed when the universe was only about 6 billion years old, less than halfway through its current age. Early analyses found it was approximately 6 times more massive than the most massive cluster standard cosmology predicted should exist at that point in cosmic history. The probability of El Gordo forming when and where it did, under standard cosmological models, was estimated by some researchers at 1 in 10 million. More recent measurements revised the mass slightly downward. It's now considered just barely consistent with standard models, marginally, tensely, uncomfortably consistent. It remains one of the most significant tensions in observational cosmology. When the James Webb Space Telescope turned toward El Gordo in July of 2022, it found more. Gravitationally lensed galaxies behind the cluster, their light bent and stretched into arcs by the enormous mass in front of them. One of these arcs was nicknamed La Flaca, the skinny one. An object billions of light years behind El Gordo, its image smeared across the sky by a mass so large it bends space like a lens. An object that, by the universe's own rules, should not have existed yet. And yet, everything so far has been objects you could point a telescope at. Something with coordinates, something with edges. The next two are different. They are so large that the question stops being what is this and becomes what does this mean? Number 4. Porphyrion. A single black hole drew a line across the universe. Somewhere 7.5 billion light years away, a black hole started eating. It ate continuously, steadily for approximately 1 billion years. And while it ate, it did what active black holes sometimes do. It launched 2 jets. Plasma, accelerated to near the speed of light, blasted outward from both poles simultaneously. Those jets are still there. They span 23 million light years from end to end. Let that sit for a second. 140 Milky Way galaxies laid side by side. That's the length of a structure built by one black hole's activity over 1 billion years. When astronomers discovered it in 2024 and named it Porphyrion after a giant from Greek mythology, the lead researcher said, "The Milky Way would be a little dot in these 2 giant eruptions." The same team had found a different record holder just 2 years earlier. That one was 16 million light years. They beat their own record by 7 million light years. And then later in 2024, someone found another one even bigger. This field is moving extraordinarily fast. What makes Porphyrion genuinely strange is not just the size, it's that it's almost perfectly straight. Something 23 million light years long, firing through a universe full of gas clouds, magnetic fields, gravitational distortions, and the general chaos of the cosmic web, and it barely bends. Nobody knows why. There are theories involving the density of the intergalactic medium, the orientation of surrounding filaments, the age of the jets. No consensus. What we do know is what it implies. Porphyrion existed when the universe was about 6 billion years old, when the large-scale structure of the cosmos, the cosmic web of filaments and voids, was more compact than it is today. Porphyrion's jets were long enough to reach 2/3 of the way across the void between filaments. This means the plasma, the magnetic fields, the energy from one black hole's feeding spread across a significant fraction of a cosmic void, seeding it, changing it. The lead researcher's conclusion: every place in the universe may have been affected by black hole activity at some point in cosmic time. Not some places. Every place. The black hole wasn't inside the universe, acting on local material. It was reshaping the architecture, one object, one exhaust. Universe scale consequences. Number 3, the Hercules Corona Borealis Great Wall. The structure cosmology says shouldn't exist. Modern cosmology is built on an assumption, a foundational one. The cosmological principle that on large enough scales the universe is smooth. Matter is distributed roughly evenly. No region is dramatically different from any other. This isn't a guess. It's backed by decades of observation, confirmed by the cosmic microwave background, embedded into every major cosmological model we have, and it has a precise prediction. Above roughly 370 million light-years, the universe should stop having large structures. It should average out. Cosmologists call this the end of greatness. The Hercules Corona Borealis Great Wall is 10 to 15 billion light-years across. That is 25 to 40 times larger than the theoretical maximum. It covers roughly 1/8 of the entire observable sky. It was discovered in 2013 by a team of American and Hungarian astronomers analyzing the distribution of gamma-ray bursts, some of the most violent explosions in the universe, each one marking a region of dense matter. They found a cluster of these explosions all at the same distance, concentrated in the same region of sky, in a pattern that couldn't be explained by chance. The structure they propose to explain it is enormous enough that our standard cosmological model simply cannot produce it, not by a small margin, by a factor of 25 or more. Here's a detail that's easy to overlook. The name Hercules Corona Borealis Great Wall was coined not by the discovery team, not in a journal, but by a Filipino teenager from Marikina who read about the discovery on the internet and added the name to Wikipedia. Astronomer John Hakila, one of the lead researchers, later began using the name in his papers. A structure that may require us to rewrite our model of the universe got its name from a kid on Wikipedia. In 2025, the same team reanalyzed the data with a larger sample, 542 gamma-ray bursts instead of 283. The result? The wall may be 50% larger than previously thought. 15 billion light-years. And the closest parts of it are closer to us than they originally estimated. The problem isn't shrinking. It's growing. Is it real? This is genuinely contested. Some researchers argue the clustering is a statistical artifact that with enough redshift bins, you'll always find something that looks like a pattern. The discovery team argues their statistical thresholds are appropriate. A proposed satellite called Theseus, if it ever launches, would detect thousands more gamma-ray bursts and likely settle the question. But if the Great Wall is real, and the evidence increasingly suggests it is, then the universe is not smooth at large scales. The cosmological principle, the assumption at the foundation of modern cosmology, is wrong. Not slightly off, wrong. That question used to be about how big things could get. Now, it's about whether the universe follows its own rules. Number 2, the observable universe, the object with a built-in horizon. It is 93 billion light-years across. Not because the universe is 93 billion light-years old, it's only 13.8 billion years old. The number is larger because space has been expanding the entire time light was traveling, stretching the distance between its origin and us. The universe is bigger than its own age would suggest. Inside it, roughly 2 trillion galaxies, approximately 10 to the power of 80 atoms, all of it visible to us only because light had time to reach us. Beyond that horizon, more universe, possibly infinite, almost certainly vastly larger than what we can see. Here's the problem. Multiple problems, actually. The universe is geometrically flat, meaning its total energy density is tuned to within 1 part in 10 to the 60th of the exact value required for flatness. Any deviation from that value at the moment of the Big Bang, more energy, less energy, even slightly, and the universe either collapses back in on itself immediately or expands so fast that matter never clumps together, no galaxies form, no stars ignite, nothing happens. It's balanced on a knife's edge that makes no physical sense unless something forced it there. The cosmic microwave background, the afterglow of the Big Bang, detectable in every direction, is uniform in temperature to roughly 1 part in 100,000. Regions of the sky separated by billions of light-years, regions that could never have been in contact with each other given the speed of light, are at the exact same temperature. They had no way to synchronize. And yet they match. The standard explanation is inflation, a period of faster-than-light expansion in the first tiny fraction of a second after the Big Bang that would have stretched a small uniform region into the entire observable universe. But inflation has never been directly confirmed. And then there's this. Quantum field theory, our best description of fundamental physics, predicts a value for the energy of empty space. The actual observed value of that energy, inferred from the expansion rate of the universe, is approximately 10 to the power of 120 times smaller than the prediction, one followed by 120 zeros. This is often described without exaggeration as the worst prediction in the history of physics. The observable universe is not just large, it is, in multiple independent ways, physically inexplicable under our best models. Number one, the answer, there is no number one. This is not a dodge. It's the actual point. Stephenson 2:18 breaks stellar structure. A star larger than physics says stars can hold together. Neutron stars break matter itself. Density past the point where normal physics applies. SGR 180620 breaks electromagnetism, a magnetic field that rewrites atoms and distorts space. TON 618 breaks accretion, a black hole that exceeded the theoretical maximum for how black holes grow. IC1101 breaks galaxy formation, a galaxy whose black hole overshot every prediction for its own mass. El Gordo breaks cosmic timing, a structure too massive for the age of the universe it formed in. Porphyrion breaks the boundary between object and structure. One black hole's exhaust reshaping the architecture of the cosmos. The Great Wall breaks cosmological homogeneity, a structure that should not exist getting larger every time we look. The observable universe breaks quantum field theory, an object whose basic properties our best equations cannot explain. These aren't 10 versions of the same problem. There are 10 different places where the universe exceeded the equation we wrote for it. The pattern across all of them is the same. We find a limit. We confirm it with math. We publish it. And then the universe produces something that sits past it, indifferent, enormous, doing whatever it wants. The question isn't really whether these objects break the laws of physics. The question is whether those laws were ever complete to begin with. The universe doesn't care about our equations. It just keeps building things we don't have words for yet.